Hello, this is Professor Kuehn. Welcome back to my discussion of Einstein's theory of relativity, where we've been talking about time dilation. You might remember in our last lecture, we were talking about a spaceship on which a man named Luke is riding, and John, an astronaut who is watching the spaceship rush by at a speed v. We showed that the clock that is on Luke's spaceship, that consists of a ball bouncing back and forth between two bumpers, has a tick every time that's equal to 2d over u. That is twice the distance across the ship divided by the speed of the ball moving within the ship. And we showed that the clock is also ticking, as measured by John, at the exact same rate. That is twice the distance across the ship divided by u, the speed of the ball. Notice that this relied on adding the ship's speed to the speed of the ball itself according to ordinary velocity addition rules. This means that the ball had to move farther, as measured by John, but it was also moving faster. And so what ended up happening is that Luke and John agree on the time between ticks of Luke's clock. Now what I want to do is talk about another kind of clock, a special kind of clock that you might call a light clock. So imagine that instead of this ball bouncing back and forth, we were to construct a clock made of two mirrors. So imagine that we have a clock, maybe it'll look a little bit like an hourglass. Oops, like this. And this clock ticks every time a beam of light, which leaves a light source down here, travels upward, bounces off this surface, and comes back down. I'm trying to draw that in a straight line, and hits. And there's a tick every time it hits the bottom. Okay? So now if we substituted this clock for the clock on the ship, how would the situation change? Well, the time between ticks of Luke's light clock, according to Luke himself, would just be the distance that the light moves up and down, which would be, once again, 2d, divided by the speed of light, which is c. So that would be the time between ticks of this clock as measured by Luke. Now, what would John measure? What would be the time between ticks of Luke's clock as measured by John? Well, delta t John is equal to twice the distance the light travels. But now notice that this light beam, according to John, he sees it moving upward. It is going to be moving at a diagonal. It's going to bounce off this surface and come back down like this. So it is going to move, once again, a distance 2s, divided by the speed it's moving. And here is precisely where things are different. One does not add the speed of the ship v to the vertical speed of the light, because the speed of light is the same for all observers. That means that the speed of light is c in this case, once again. So although the distance it moves is farther, the speed it moves is the same, and that's going to give rise to the phenomenon where delta tj is going to be bigger than delta t Luke, delta tl. That means if, let's say, Luke measures 1 millisecond between ticks of his own clock, John, when looking at that clock, will maybe measure 1.5 milliseconds between ticks of Luke's clock. So he will perceive that Luke's clock is ticking more slowly. That is, there's more time between ticks. So John will observe Luke's clock to be ticking slowly. That is the phenomenon of time dilation. Okay? How much slowly is it ticking? So what I want to do is I want to go through a short mathematical derivation to show the relationship between the ticks of Luke's clock as measured by Luke and the ticks of Luke's clock as measured by John. So here we go. This is going to take a little bit of work, but it'll be worth it. Delta t John, once again, is 2s over c. What is 2s? Well, we can do this exactly like we did last time. 2x squared, where x is the horizontal distance it moves, over d squared over c. Well, what was this distance x? Well, once again, that's the speed of the ship times the time interval between ticks as measured by John divided by 2, because it's half of a time interval, squared plus d squared. divided by c. Now what we want to do is get all these delta tj's on one side of the equation. So to do that, we're going to square both sides. Delta tj squared is equal to 4 over c squared times delta tj squared v squared over 4 plus d squared. And now what we're going to do is multiply this out and move all the delta tj's over to one side. I'll just do this in one step. Delta tj squared times 1, that's from this term right here, minus this stuff right here where the 4 is going to cancel the 4. We're going to end up with v squared over c squared. And on the right hand side, we're going to be left with 4d squared over c squared. I'm just doing algebra. I skipped a step there, so you might want to look at how I did that. And now finally, I want to divide through by the amount in the parentheses. Delta tj squared is equal to 4d squared, well, I'll say 1 over 1 minus v squared over c squared times 4d squared over c squared. And now, of course, we can take the square root. Delta tj is equal to 1 over the square root of 1 minus v squared over c squared times 2d over c. So notice what's happened here, that the time between ticks of Luke's clock as measured by John is different than the time between Luke's clock as measured by Luke. And it's different by the amount in these parentheses. This right here, notice, just is the time between ticks of Luke's clock as measured by Luke himself. So we can write this as delta t, John, is equal to this factor, and this factor is sometimes called the gamma factor, times delta t, Luke. So there's a correction factor that depends on the speed of the ship compared to John. And that is the amount by which the clock rates of ticking differ. Okay? Sometimes this formula, if we don't want to use Luke and John specifically, we can write this formula in a little bit more general form as delta t, the time between ticks as measured by someone like John, who's watching the clock rush by, is equal to gamma times delta t naught, where gamma is equal to 1 over 1 minus v squared over c squared square root. These are important formulas, and in my next lecture I'll come back and I'll talk a little bit more about this.